Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're done with talking about the formation of stars and protostars, and now we're going to actually see how low-mass stars like the Sun evolve with time. And stars themselves change with respect to their course of their histories and how they actually evolve as they use up their fuel from the moment they are born. So let's look at exactly how that's done. The thing we got to remember is that most of the all the stars in the sky are really quite boring. Most of the stars are insanely boring because less than half the mass of the Sun. They do some really boring stuff that we'll look at the end. It only takes one slide to explain it. So 85% of all the stars in the entire Milky Way can be explained with one slide after we're done talking about the Sun. But we're going to then go back and later things look at the really more dramatic things. Such as massive stars that populate the cosmos with heavier elements. But what we'll talk about this time is how a star like the Sun changes with time. And so once again, let's start over with the life cycles of stars. This comes from the Chandra group, and we see that the mass goes from the low mass stars from the bottom of this graph and the high mass stars from the top of this graph. And as time progresses from left to right, we see that there's different flavors of protostars. The more massive the protostar, they do something slightly different. And so we're going to be talking about the bottom three tiers, which are the brown dwarfs, which don't really serve much of a purpose. So we're just going to say right now what happens to a brown dwarf. It's less than 8% of the mass of the Sun, or 0.08 solar masses. It does not initiate fusion in its core. It just simply contracts like a protostar under gravitational pressure, and that releases heat, and it does that for a very long time. And it becomes a brown dwarf, and forever it is a brown dwarf. It does nothing. But we will talk about red dwarfs, which then eventually become white dwarfs. But we're going to look at the third tier, which is a Sun-like star that starts from a protostar, becomes the Sun-like thing, becomes a red giant, forms this thing called a Planetary Nebula, and a white dwarf. And we'll talk about some of the other stuff later, but the top bunch we will talk about next time. So the life cycles of stars tell us how stars are born, how they live, and how they die. So the source of the life of a star is hydrogen fusion in its core. Every star that you see in the night sky, every single one of them is fusing hydrogen into helium in its core at least. Some of the other brighter stars, such as Betelgeuse or Bellatrix, might be fusing helium in their cores. But our real question today is, what happens when hydrogen is done? When after helium is created? Well, for stars like the Sun, right now the core is too cool to ignite helium fusion. It's just not hot enough. And therefore, an inert helium core is slowly building up in the center of the Sun. For the Sun, the main sequence lifespan, which is the same thing as saying it's burning hydrogen. We say burning, but mostly we mean fusion, so I'll loosely conflate the word burning with fusing. So hydrogen fusion or hydrogen burning, the lifetime, is the main sequence of a star. And the Sun will go about 10 billion years if it's about one solar mass. That's what that M sub target means. That means one solar mass. But if it's a tenth the mass of the Sun, then it can live up to 10 trillion years, or 10 to the 12th, or 10 to the 13th years. It can live a long time, and these are the red dwarfs. They're really incredibly boring, incredibly dim, but they're the most common star of all. So the evolutionary cycle of the Sun kind of goes with that peculiar graphic across the top. For about 10 or 11 billion years, the Sun is a mean sequence star. Then for about 1.25 billion years, it's a red giant. Then it becomes what we'll talk about, a horizontal giant branch star for about 100,000 years, an asymptotic giant branch for about 20 million years. It'll pulse itself apart over 500,000 years, and it will become a planetary nebula for only about 10,000 years. And at the end of its lifespan, it will be a white dwarf, about half the mass that it started off being. Right now, the Sun is about 4.5 billion years into its life of approximately 11 billion or 11.5 billion years, and that's what we're going to talk about. So in the center of the Sun right now, there's hydrogen core burning, and it's fusing hydrogen into helium, and the process is predominantly the proton-proton chain, and that's what it is roughly at 15 million Kelvin, which is in the core. If it was a little hotter, maybe about 18 million Kelvin, then the Sun would be burning through the CNO cycle. but right now it is currently using the carbon, nitrogen, oxygen cycle. I think we talked about that before, but we'll talk about it again later in later talk. So right now it's going to be doing this for about 11 billion years. And the structure of the sun is as an inert helium core down in the core. It just kind of sinks to the center. That's not participating in anything, and all of the core is completely composed of helium. Surrounding it is a hydrogen burning core, and surrounding that is the radiative zone, which is kind of reddish there, and then the convective zone, which would be yellow, that we see today, which is the granules and supergranules in the sun, as well as all the active regions on the surface of the sun. But when it starts to run out, that's what we call leaving the main sequence. Because on the main sequence, there are two things that are always in balance. One, there's a gravitational pull that's pulling the star together, and it's balanced by the outward pressure because of the heat from the center. So if it heats up a little bit, so we got to remember the balance now. If it heats up a little bit, the star will expand. And once it's expanded, then it'll cool down in the core. And when it cools off in the core, then it'll start contracting again. And so therefore, this is kind of a normal balance. And once it contracts too much, it'll heat up too much and it'll expand again, just like a normal gas. This is a balance in equilibrium. So a thermal balance and a hydrostatic equilibrium and a thermal equilibrium. So when it leaves the main sequence, the appearance of the star changes. I'm not going to go through all of this to the important things, but basically the temperature rises in the core, the temperature rises on the surface, or at least cools on the surface, then radically rises. We'll see why that is. The diameter of the sun radically changes and gets extraordinarily large, and the central temperature steadily climbs, even though the surface temperature steadily drops, which is interesting. And each successive stage is shorter and shorter and shorter in the sun's life. So how does the sun evolve? So what we do is that researchers using computer codes create models using those equations that I showed you in a previous lecture for stellar interiors and for the equations of hydrostatic equilibrium and the equations of stellar structure. All of those things can be plugged into computer codes, and you look at the exterior of the sun, the mass of the sun, the luminosity of the sun, the composition of the sun as we see it on the surface, and then we run it backwards in time into the center of the sun in order to get the central conditions. And that is called a computer model. So all of the computer models that give us the numbers of the star, then we can make a map of the inside of the star and see how changes in the core of the star affect the changes on the surface of the star. And so here are a couple of recent articles. They're not that recent, but there's been many others. But these are some typical models that can be done. And let's start it off. So we talked last time about the nature of protostars. And the sun took about 50 million years to form from a big molecular cloud. And that core, such as like Barnard 68 or other kinds of large molecular clouds, took about 15 million years to collapse down into a star. It reached the main sequence about 4.5 billion, and we're going to use MYR, meaning million years, and GYR, meaning gigayears. So MYR means 10 to the 6th years, and GYR means 10 to the 9th years. So those are our abbreviations for today. And when the sun first dropped onto the main sequence, where it has been since we would call its birth, we call that the zero age mean sequence, when full hydrogen initiation occurred, and there was thermal equilibrium as well as hydrostatic equilibrium. Once all those three things were satisfied, then the star can be called a zero age main sequence star. Now, at that time, the sun was a bit fainter. It was only about 70% the current luminosity that it is today. It was also a little bit smaller, about 90% of its current radius, and it was actually a little cooler. It was under about a few hundred degrees Kelvin cooler, 200 Kelvin cooler at its surface than we see today. So that's the zero age main sequence for a single solar mass star. And so I'm going to we're going to plot the evolution of the sun on an HR diagram. So we have, of course, on the left-hand side, the luminosity of it, as well as the temperature, so just like our standard HR diagram. Now, the sun today About 4.5 billion or gigayears later, 4.55 times 10 to the ninth years later. Actually, it's well understood that the sun is about 4.567 billion years old, so we'll stick with that. The current mass is about 2 times 10 to the 30th kilograms, and that's what it's going to stay until it's dead, until it starts doing the throes of old age, when it actually will lose a significant amount of mass. The current radius of the sun is about 700,000 kilometers, which is about 100 Earth diameters, 100 Earth radii. And the luminosity of the sun is about 4 times 10 to the 26 watts, which is much more than the human race puts out in trillions of years. The temperature is about almost 5,800 Kelvin, and half of the core the core in the hydrogen has been fused to helium at this point. So there's an enormously large inert helium core in the center of the sun today. And the sun right now is in a state of hydrostatic and thermal equilibrium, meaning that energy that's coming out the surface is being balanced by energy being produced in the core, and the sun's not getting radically larger or smaller. It's not pulsing in any way, literally radially pulsing in and out. So it's in both hydrostatic and thermal equilibrium. So during its main sequence life, we have the convective zone on the outside, radiative zone between that and the core, and the inert core right now. And the inert core is actually small compared to the hydrogen-burning core, but that would comprise about half of the mass of the core, that purple nugget in the center. So as the sun evolved, it started off as the top one, where we see that it was about 75% hydrogen, about 25% helium, or more like 85% hydrogen, 25% helium. That's kind of what it is at the sun's helium abundance by percent of each element. So that would be the total number of elements per particle would be what we're looking at now, and rather than by mass, because if it was by mass, we'd be about 75. But we're looking at per particle. About right now, the distance from the core shows you what the helium nugget looks like. And we see that it kind of is a smooth distribution from the middle thing, meaning with the core has a certain diameter, and that's where the helium is, and that's how we're kind of defining the core, is where fusion reactions occur and where the helium is building up. So the center has a little bit less helium because it's so incredibly hot that some of that's getting driven out a little bit. But after about 10 billion years, the core will expand, and it will be then all of the hydrogen will be gone in the core. And there will be literally none in the core of hydrogen. But the helium will then be layered on top, and that little nugget will be extraordinarily large at 10 billion years. But even still after 10 billion years, most of the star is made out of hydrogen. And if we think the size of the sun is about 700,000 kilometers, even at the surface, we won't see an abundance of helium percolating up. That's because there is no mixing from the core up to the surface for stars like the sun. Remember, between the core and the outer regions is a radiative zone where there's not a lot of flow, where the photons just travel radiatively rather than convectively. So right around 350,000 kilometers from the core, it still is flowing radiatively. Energy flows radiatively. There's not a lot of burbling and bubbling. That only happens at the top layers, right around 500,000 kilometers or 400,000 kilometers and up, where the convective layers live in the sun. So there is no mixing of the core helium to the surface. All right, so as the sun runs out of hydrogen, we're going to kind of repeat this a couple times. It's just the nature of this particular talk. We'll repeat things a couple times. The helium core collapses, meaning it starts to get smaller and smaller and smaller, and it heats up. And it heats up extraordinarily rapidly, but it does not actually ignite helium fusion. The hydrogen burns in a zone around the core. It's a very thin shell around it because there's no hydrogen left in the core. And that means because there's less of an area where it's actually occurring, less of a volume, then the fusion, in order to produce the heat, in order to stay in equilibrium, it has to go faster. If it has to go faster, it has to get hotter. In order for it to get hotter, that means greater luminosity. If it has greater luminosity, then the star must expand. And so therefore, the star starts to grow in order to accommodate the increased luminosity coming out of the core. And so therefore, it becomes a red giant. So by the time it becomes a red giant, there's an enormous envelope around it. There's a hydrogen-burning shell and an inert helium core that's not yet burning, or at least fusing helium into anything. So that's interesting. Let's describe that again in more detail in a second. So at an age of about almost 11 billion years, about 6.25 gigayears, 6.35 gigayears from today, it'll run out of hydrogen. Most of the volume of the core is helium, and the core will contract because the pressure of the star above it is heavy, and so it's pushing it together in order to, because the core will contract such that the volume around it can actually contain only hydrogen, which then participates in the hydrogen burning in a shell around the core. So at the surface, the temperature is going to drop, even though the core temperature is going to rise. And that's because the luminosity increases by a factor of almost 2, or twice as much, 2.21 times. So if the luminosity increases twice as much, that means the core luminosity has to go up. For the core luminosity to go up, that means the temperature must go up. So it's getting hotter in the center of the sun all this time. It becomes a subgiant star. Next, over the next 700 million years, or almost about a half a billion years, the sun will expand at roughly the same luminosity, and it'll become it'll stay about two solar luminosities. Then it'll swell in size, and then all of a sudden it'll start to grow really fast, and it'll become an extraordinarily fast-growing red giant star. And as it does so, it'll puff up in size. And the radius of the sun will go from 1.5 times its current radius, which is 700,000 kilometers. And so 1.5 times that is almost 1 billion kilometers. It's more than 1 billion kilometers, up to twice it, 2.5 times it. So it'll go from 750,000 kilometers all the way up to 1.5 or 1.7 billion kilometers, which is really a large star now, because it's twice the radius, 2.25 times the radius. Since it expands, the surface temperature cools, but the luminosity, remember, is large because the core temperature is high, so the luminosity is great. All right, so it'll climb the red giant branch, taking another 600,000 years to get larger and larger and larger as the core contracts and contracts and contracts and gets hotter and hotter, and the shell burning goes even faster and faster. And during this time, this red giant phase, the surface temperature, the surface will not be as bound as it is today. Remember, we talked about the solar wind when we talked about the sun. The sun always has a solar wind, but now the solar wind will be incredibly strong, and it will lose about 1/4 of its mass out to a wind pushing it away. So most of the sun will start falling apart. A big chunk of it, 1/4 of the mass, will be gone. And that's because as it expands, it's farther away from the center of gravity, which means if it gets energy, it's easier for it to escape. And all you have to do is get it hot enough so that it escapes. So there will be huge pulses of clouds that will come off the sun in an enormous, enormous wind as it becomes a red giant. So remember again, the helium core contracts and heats, but still doesn't participate in fusion. But what's happening in the core is the electrons become a degenerate gas. And that means they're basically stacking up on top of each other, unable to move, both physically in place and even relax any of their energy. So they actually get packed down to such an extent that it's almost like they don't have a temperature. They almost get to the point where they're stacked like bricks. So the electrons are almost incapable of moving. So it's almost like they have no temperature. The protons, though, are more massive, so they actually act like a normal gas, and so they get hotter and hotter and hotter. But the hydrogen burning becomes a shell around that core, which is now a degenerate electron gas, which is a funny thing to say. And the huge puffy envelope of the star becomes almost the size of the orbit of Venus. So Mercury is gone. It's dead. It's been eaten by the sun. And if it gets out to the size of Venus, then Venus is dead. It'll go into the sun, and that's the end of the planet Venus. Likewise, that's probably the end of the planet Earth too, because once you get to that size, there'll be a huge amount of wind that'll drag on the Earth. It'll provide friction, and the wind, as the Earth travels through this enormous wind of gas coming off the sun, it will spiral into the sun at this time and disappear as part of it. So the inner solar system will be cleared of planets at this time. including the Earth. So this is how the Earth dies. So at the tip of the red giant branch, isn't that a funny thing to say? That's such a terrible thing to say, but that's what we're going to say. The Earth is dead when the sun becomes a red giant. So the tip finally becomes the tip of a red giant branch. A huge change occurs, and the core of the core temperature has been getting hotter and hotter and hotter, and finally it reaches about 100 million Kelvin, and that ignites all of the helium burning all at once in what we call the helium flash. And this happens when the sun has cooled at its surface to become an M0 star. It's a giant star, and the temperature has dropped to well about 3,000 Kelvin, about half its current temperature. But the luminosity is now almost 2,000 times that, and the radius is almost 200 times its current radius. And that's big. That's about 3/4 of an AU. That'll swallow Mercury. That'll swallow Venus. That'll be the end of that. So that's a big, big, big star. Red giants are big things. So now the sun is a red giant at this late stage in its life. And when it does reach that, all of the helium starts burning carbon to oxygen, ignite extraordinarily rapidly in what's called the helium flash. And the helium flash occurs because the protons are getting hotter and hotter and hotter. They're moving faster and faster. The electrons are getting more and more and more compressed. They can't move. And so they're in what's called a degenerate state. This degenerate state needs to be lifted away when it gets hot enough, so that when fusion starts to occur, it releases more energy, which can be given to the electrons, and therefore they can participate in the support of the star. And so now we go after the helium flash, where this all begins at once. We then move down to what's called the helium main sequence, or the horizontal branch. So once again, the triple alpha process now is coming into play, which is at 100 million Kelvin. The triple alpha process, which is the fusion of helium nuclei into carbon and then into oxygen. The first step is to slam two alpha particles, which are helium nuclei, together. They form beryllium, which is incredibly unstable and it will disintegrate almost immediately. But if the density is high enough and another helium nuclei comes along fast enough, then they'll collide together to form carbon-12. And carbon-12 then can collide with the another helium nuclei to form oxygen-16. So these little starry things indicate collisions, and beryllium can fall backwards and forwards. It can go from this and into the other. So beryllium is very short-lived. It's barely together, and only thing that's producing energy out of this thing is the collision of the beryllium with another helium nucleus to give a gamma ray photon, or a carbon nucleus with a helium nucleus to form an oxygen nucleus, which also gives gamma rays. And those gamma rays are what the thing that actually provides the energy. So the star then is hot enough to burn the helium, but this is not efficient. It's not even remotely as efficient at producing energy as hydrogen fusion into helium. So you get all this additional hydrogen burning around. You get core helium fusion, which is extraordinarily sensitive to temperature. Then you have hydrogen burning around the shell, and the star shrinks a bit because now it can shrink. So as it shrinks, it raises the temperature, it shrinks in radius, it gets fainter, and it goes back to hydrostatic and thermal equilibrium again, using triple alpha process as its primary source of energy. The sun descends back onto the horizontal giant branch in about 1 million years. The internal structure rearranges rather rapidly to accommodate the energy, and now the helium is burning at the core. It stabilizes everything against the collapse, and then there's still some hydrogen burning around because, the star is mostly hydrogen on the outside. It's lost most of it. It's lost 1/4 of its mass so far. We're down to a 0.75 solar mass star, but that's still hot enough to burn helium in the core as it gets compressed and compressed and compressed. Again, here's our view of it, the triple alpha process. It's incredibly inefficient. It can only last about 100 million years, as opposed to the 10 billion year lifespan of hydrogen burning. That's because this process doesn't give off as much energy, and there's fewer particles now. Remember, there was like a bunch of protons, but now all those protons have formed an object that has 4 objects in it. So now 4 objects, you can think of them as bundles of 4. So you used to have bundles of 1, which became bundles of 4. And now you got bundles of 4 becoming bundles of 12 and 16. So you're rapidly removing particles from the system. The total number of particles is dropping rapidly because as you fuse them together, the numbers reduce. The total number of objects reduce, and because now they're sticking together. But they're still too cool to ignite the carbon fusion, significant carbon fusion into oxygen, but there's some oxygen fusion. And there's very little carbon and oxygen, nothing going much past oxygen at this point. So this is the horizontal giant branch for helium fusion for the sun. Now at this time, the sun's radius will be about 10 times its current radius. The temperature will still be much cooler than it was on the main sequence, but its luminosity will be about 40 times its current luminosity. So it'll still be much brighter than it was. It'll be much bigger than it was, and that's the nature of a horizontal giant branch star. These are all giant stars, which are not main sequence stars, but the main sequence we're talking about now is a main sequence for helium burning, not a main, which is the horizontal branch, not a main sequence of hydrogen burning. The helium fusion is much less efficient, so it can only last it'll last a much shorter period of time, only 100 megayears or 100 million years. After this 100 million years, it again slips out of equilibrium. The carbon-oxygen core, ash core, begins to contract, just like the helium core did previously. And then there's a helium burning shell around that core, and then a hydrogen burning shell around that helium burning shell. So it's a little bit of an onion shape. It swells up again, becoming a giant once again, raises its radius to about 20 times the radius of the sun, cools off some more, luminosity grows again. Remember, the luminosity is a result of the temperature increasing. So the higher the temperature in the core, that provides greater luminosity in the core. Greater luminosity in the core means the rate of reaction is going faster in the core because stuff is running out. And so they're trying, the reason the luminosity goes up is because since the temperature must go up because there's fewer particles, the particles have to move faster in order to literally find each other and in order to do the fusion. Since there's fewer particles with which they can collide, they must go faster, which means they have to go farther, literally farther inside the star at a faster speed in order to collide with each other so they can actually provide the energy to balance against gravity. So it's a big race. It's a huge race against gravity and the pressure due to gravity. So it again climbs up what we call the asymptotic giant branch, and over 20 million years, the carbon-oxygen core contracts and contracts and contracts even more and heats up even more. The fusion moves out into a very strong shell. The thin hydrogen shell is way outside the helium-burning shell. And on the outside, the sun swells up, gets even bigger, gets almost as large as the Earth's orbit, gets to be about 84% of the Earth's orbit. The Earth's been gone long anyway. It went down the first time, but now it's probably Mars's turn to go under, even though it's at 1.5 AU. There'll be enough drag from the wind from the star they'll probably plunge into. And the temperature will again cool off at the surface to 3200 Kelvin. But the luminosity is much greater. So the high luminosity belies the incredible temperature at the core. So even though the surface temperature is only 3000 Kelvin, the core temperature is well over 100 million Kelvin. And it's even brighter than it was when it climbed the giant branch before. And again, because it's brighter, it will live a much shorter time span on this thing. All right. So then after 100,000 years, again, it collapses and forms that shell. There's the helium shell burning on top of it. There's the asymptotic giant branch we're looking at as a thin line instead. And we're watching it track across the HR diagram. So this is what we call an evolutionary track. The main sequence line that's going from upper left to lower right is just a reference point. But the black line that leaves the main sequence goes up the red giant branch to the horizontal branch and then up the asymptotic giant branch. That's the track of evolution for the sun. And so each of those things, it goes different rates of speed along those tracks, but that's the track it would take if we could watch its luminosity and temperature change from a safe distance as the star evolved over billions of years. All right, so once it gets to the asymptotic giant branch, it is now a red giant for the second time. It's cooler, larger, and more luminous. And there's an enormous inert carbon and oxygen core with a helium burning shell around it, a hydrogen burning shell around it. And the red giant envelope is, of course, enormous at about 200 times the radius of the current sun now. What's funny about this is helium burning is incredibly sensitive. So to actually make that ash, that green ash with carbon and oxygen in the core and the purple area that we see there, it's incredibly temperature sensitive. And so the fusion rate goes like the temperature to the 40th power. So if you raise the temperature only by a little bit, maybe 10% when it's 100 million Kelvin, then the fusion rate goes up 45 times. And if the temperature doubles, it'll go up, wow, almost a quadrillion times. So that's a huge jump in fusion rate. So if you increase the temperature just a little bit, you get these enormous changes in the rate of production. So a small change makes these thermal pulses. So I made those arrows to show that all of a sudden there's enormous heat that all of a sudden pushes out from the center, lifting the envelope away, and it destabilizes the envelope of the star, and that makes the core and the envelope separate. And as a result of it, the entire outer envelope is ejected as a fast wind over 100,000 years, which is essentially the entire lifespan of known human history, is about 100,000 years. The carbon-oxygen core continues to contract, but outside of that is an enormous, brightening, hot, moving shell, and it'll take about 5 or 6 or just a half a dozen or a handful of these pulses to completely separate the outer shell of the star into the cosmos. But the star's core still stays there. It's still remaining super-duper hot. It just never, and it doesn't get bigger because it's pushed together now. It's now a huge thing. It's self-gravitating. It's not going to just expand because it's gas. No, it's going to be it's very dense. It's extraordinarily small. It's been pushed together, and the temperature is incredibly high. However, it's not so high that carbon fusion ignition occurs, which occurs for much higher temperatures. So the asymptotic giant branch phase exhibits enormous mass loss as a result of these thermal pulses. And now we're down to about 60% of the original mass. So now 40% of the sun's mass is now gone, with the quarter of it gone in the initial part. So we've got expanding shells in the first group, and now we have even more expanding shells of hydrogen gas and some carbon and some helium puffing away, because those thermal pulses do bounce a little bit off the bottom for some stars. And so we see the enormous mass loss coming off of the star. There'll be about 4 or 5 or 6 puffs, maybe up to 7, depending on the computer model, and roughly about 100,000 years between them. And each puff sends the sun to a much larger radius. The sun contracts, and then all of a sudden it blows the outer layer off as it gets just hot enough in order to do so. And that's because of that enormous temperature gradient that I showed you, the temperature sensitivity that I showed you. So it contracts and makes like a really tight blanket, and then just like a little kid who has tons and tons of blankets on just kicks them all off. And that's what it does. It's a kicking off of all your blankets, and it pushes them off the bed, basically. And so they go out into space, and they're left out with something, with the remaining envelope expands away. The last of the thermal pulses pushes what's left of the outer envelope over the course of a couple thousand years, and it's left with the bare carbon-oxygen core down there. So the surface of the sun, the luminosity, the shell goes from about the star from the outside. The envelope looks like about 4,000 Kelvin, shielding the inner core. And now we see the bare core of the star, which is over 100,000 Kelvin. And the luminosity stays roughly about constant. It's about almost 3,500 times the luminosity of the sun, between both the glowing material that's coming off of it and the core of the star that remains. And the outer glowing shell is called a planetary nebula, and that's kind of a funny term. But the bare core then ionizes the outer shell. All of the atoms become ionized. They're very diffuse, and so they emit specific. They make an emission spectrum. And the emission spectrum of the gas is called a planetary nebula. And so this is the state of affairs after 12 billion years of the sun's history. The expanding envelope it forms a nebula around the contracting core, and that's ionized by the central core, and that thing just goes out into space and becomes nothing, and you mixes with the rest of the interstellar medium. So this hydrogen, some of the helium, and a little bit of the carbon and oxygen that was in the core gets diffused out into the cosmos and becomes part of the interstellar medium again by these thermal pulses of the sun, or what that it will do, and that will be the seeds of future stars. And the star becomes a host to a planetary nebula, and the carbon-oxygen core is exposed, and that's called a white dwarf. So the planetary nebula then is the glowing outer shell that I showed you before, plus that like flowery shape, and these things are seen in the sky. And one of the most prominent ones is called the Ring Nebula, which is in the constellation of Lyra. And you see the glowing gas around it, and the white dwarf in the center. And the glowing gas used to be the envelope of the star, and the white dwarf is the thing that's ionizing into the core. That's the core of the star, and that's over 100,000 degrees Kelvin. 100,000 Kelvin. I shouldn't say degrees Kelvin. It's just 100,000 Kelvin. That's so incredibly hot that it's ionizing all that gas. And that gas then glows as a result of it being irradiated by the huge amount of ultraviolet photons coming off of the white dwarf. And then the atoms, and their atoms now, pick up the electrons, take that ultraviolet photon, are ionized from the atom, and as they cascade back down into the atom to be reabsorbed or combined back to atoms, then it gives off the light that we see from the Ring Nebula. And this was taken. This is called M57. This is one of the great images by the Hubble Space Telescope, and this is a Hubble Heritage image. And it's kind of a funny thing. If we look, there's a special filter called an O3 filter that you can get for a telescope. And if you look at planetary nebula with it, they're actually much clearer with this filter. And that filter allows you to actually see these nebulae and pick them out a little easier in a telescope if you're using it. Also, there's a number of there's lots of ionized nitrogen in this field, as well as ionized helium, and so forth. And so this bubble shape is what we expect from something like a planetary nebula from a star that's dying. And there's another one, which is the Helix Nebula, one of the more prominent planetary nebulae. It's enormous, about 700 light years away, and the size is across it is about 3 light years. So as the star is expanding away, or the outer layers are expanding away, the white dwarf at the center is so incredibly intense in ultraviolet light that it can ionize gas out to a distance of 3 light years. So once again, if you happen to take a spaceship and fly right next to that white dwarf right now, take the Doctor Who TARDIS and go over there and open up the gas, the air inside of your spaceship would be ionized and turned to a plasma ionized gas inside your spaceship, and your skin would be slowly ionized and evaporate away. Yeah, another name for astronomy classes is A Million Ways to Die, which is kind of a funny name. But the Helix Nebula is also a wonderful target for telescopes, and this was taken by the Hubble Space Telescope. Here are other photos of planetary nebulae, and planetary nebulae are incredibly important things because they tell us about how stars die, and they also tell us about maybe there's a stellar companion, because some of these things have these strange curlicue type shapes, which might be occurring because there's a secondary companion that is interfering with the expansion of the gas, or maybe the star itself was rotating incredibly quickly, or the thermal pulses were not even from the center, and they were not smoothly distributed across the white dwarf as the thermal pulses were occurring. So it's an area of active study as to exactly how planetary nebulae form, and there's some really amazing things, and they're fun to find in telescopes. And this was taken by the Hubble Space Telescope after the 2009 servicing mission. And this is the Bug Nebula, or NGC 6302. And the winds from these, we think, oh, just a stellar wind, wada, wada, wada. No, these winds can go incredibly fast, up to 600 or 1,000 kilometers per second. So these winds, while they look very gossamer, are actually more terrifyingly fierce than the nastiest hurricane that's ever been unleashed on the surface of the Earth. At these winds at 600 kilometers per second with a white dwarf that would ionize everything within light years of its location. And that's actually one that can be seen in the sky if you know where to look in the constellation Scorpius. So it's kind of better if you're more in the southerly locations, or if you're in the southern hemisphere, to kind of take a look at it. So as the white dwarf contracts, it becomes incredibly dense, And it is now a degenerate electron gas, which basically holds it up against the pressure of gravity. So the pressure becomes independent of the temperature. We'll talk about that pretty soon next time when we talk about the nature of degenerate gases, when I talk specifically about white dwarfs. So the pressure grows incredibly rapidly and can counteract gravity. So degenerate electron gas has the capacity to hold up an entire star. And when the star will collapse and collapse and collapse and collapse and emit more and more and more heat until it gets down to about 1/10 the current radius of the sun, or about the size of the Earth. And then that's all it does. It's just a hot, small body that's the core of a dead star. And this degenerate core is now a white dwarf. It's about half the mass of the sun, so the sun has lost almost half of its entire mass into space as a result of the planetary nebula phase and the asymptotic giant branch phase. And it just simply cools. And it takes a long time for them to cool because white dwarfs are so small that they might be incredibly hot, but they're not very luminous. They're not luminous because their size is so small. Remember the luminosity equation where we said the luminosity of a star is proportional to the surface area squared, the surface area, and the temperature to the fourth. Well, these things are incredibly hot, but they're also really small. So they don't emit, they're very dim by comparison, and so they're hard to find. And therefore, what we expect to see is that they will take a long time to cool because the surface area is so small that the energy simply can't get out. And it'll take up to 1 trillion years to fade away and stop glowing. And since the universe is only 13.8 billion years old, not a single white dwarf has turned into a black dwarf. A black dwarf is a white dwarf that has cooled completely off. The universe simply is not old enough for white dwarfs to have ever cooled off. So every white dwarf that's ever been formed in the history of the entire universe still is a white dwarf and still is incredibly hot and still is emitting huge amounts of ultraviolet light. So there's our evolutionary track for the sun. The sun starts off as a protostar, becomes, after about 11 billion years in the main sequence, becomes a giant. After it rises to a red giant, has a helium flash, drops back down to burning helium fusion, burning helium on the horizontal giant branch for a while, then goes up the asymptotic giant branch and puffs itself apart. When it puffs itself apart, it makes a planetary nebula, and that reveals the core, which is a white dwarf. So there's our evolutionary cycle for the sun, and each of those stages is shorter and shorter and shorter as it goes, with the planetary nebula being the shortest phase, so we wouldn't expect to see too many planetary nebulae in the sky, and that is exactly the case, because this phase, how long it lives, is a very short period of time. Main sequence stars live the longest, so therefore, when you look in the sky, you see stars not littered with planetary nebulae. If planetary nebulae lived 11 billion years, then we'd have all sorts of little pretty objects all over the place. But as it stands, we've got pretty stars instead. Now, if we then take a look instead, I promised you at the beginning we'd look at the really boring tiny stars and say I could do it all in one slide. Here we go. If you have a small mass star, meaning something that is little less than half the mass of the sun, then why does it last forever? It basically lasts forever. It'll last for up to 1 trillion years, 1,000 gigayears. Why? Because remember the sun, the inert helium core, had no mixing with the surface. But when a small mass star comes together, its temperature in the core is much lower. It's roughly 10 to 12 million Kelvin. And therefore the whole thing's convective. Only the outer layers of the sun are convective, and there's a radiative area that blocks the convection to flow from the surface all the way to the core. But in these little stars, they're fully convective throughout. Once it's like about less than 0.4 times the mass of the sun. And the surface goes all the way to the core, and you have convective cycles that reach to the core. So the entire star then can partake in the hydrogen to helium fusion. And because of that, that allows the star to be basically a slow cooking pot. So you think of those slow cookers where you say, oh yeah, just put in the soup and then come back at the end of the day and your soup's done, right? These are those. These are the slow cookers of the universe. And they live 1 trillion years. There's not a single M dwarf type star that has ever died in the history of the universe because the universe is only 13.8 billion years old, and these will live 1 trillion years, which is 1,000 billion years. So yeah, these are very simple little things, but remember that most of the stars in the sky are half a solar mass or less. Roughly 70% of all the stars in the sky do this, but they're very, very, very faint and very underluminous. So when we look out at the night sky, we don't see hardly any of these stars. Any of the M-type stars that we see in the sky with either binoculars or a telescope with ease are giants. All the other stars that you see in the sky are bright, bright, bright OBAF, G, and K type stars in the sky. So that's what we have for our HR diagram. We have all sorts of stars up and down the main sequence. We have supergiants, giants, and white dwarfs. That's where they come from. So this version of the HR diagram and what we saw with the Gaia mission and so forth, the reason these blocks appear in there is because the stars, there's literally billions of stars, hundreds of billions of stars, and hundreds of millions have been cataloged in their spectral type and their luminosity class. And therefore we catch the stars at their various stages in life. So when we look at most stars, we see most of the stars in the main sequence because the main sequence is the dominant lifespan of a star. When we catch a star when it's a giant, it's just leaving the main sequence. When we catch stars that are supergiants, we're looking at the most massive stars. And white dwarfs have gone through their life cycle. But anything about less than half the mass of the sun, on this graph, say 61 Cygni A or B, or less than 0.3 times the mass of the sun, those things, there's not a single star in that group that's there, which comprises 70% of all the stars in the sky, has ever died. So they're the ones that will be around for pretty much the entire universe. They will get to see it. And that gives us kind of the bottom rung of the life cycles of stars, where the brown dwarfs just stay brown dwarfs. The red dwarfs become, they don't become a red giant. They just collapse and collapse and collapse and eventually become a white dwarf. Whereas the sun becomes a red giant, a planetary nebula, and then ends as a white dwarf. And next time, we'll talk about the more massive stars, the stars much more massive than the sun, where all the other elements in the periodic table come from, where all the carbon, nitrogen, oxygen, where the platinum, gold, uranium, lead, every other element in the periodic table that lives as part of the planet Earth, that makes up the Earth, silicon, iron, everything, comes from stars that are bigger than the sun. So we're going to see what those do next time. See you soon.